Okay. Well, I'd like to start by thanking the organizers for the invitation. It's nice to be able to travel again after such a long time with COVID. So this is going to be a big switch from what we've been hearing about. This is an experimental physics talk, no computer science. But what I'll be telling you about today, as Martin mentioned, is experiments to probe new physics using AMO techniques, but physics at extremely high energy scales. So if you don't recognize this abbreviation, a PeV is 1,000 TeV. So scales that are roughly 1,000 times higher than the range of energies explored directly at the Large Hadron Collider. A way to think about these experiments is as a very specialized type of quantum sensor that's specialized to sense the nature of the quantum vacuum. And the quantum vacuum is a complicated place where there are constantly virtual appearances and disappearances of every type of particle that can occur in nature, whether we know of it directly or not. Really? Oh. Okay. I guess we'll switch. Sorry about that. No, my fault.
Oh, sorry.
Oh, okay. It looks like it's on. There we go. Okay, great, thank you. Right, so the specific way we're doing this that I'll tell you about is looking for CP-violating electric dipole moments of particles like electrons or protons or nuclei. How do we go about looking for exotic new particle physics? We take advantage of the fact, there we go, that if a particle, like an electron or a proton, has an asymmetric charge distribution attached to its spin axis. Here, for example, is an electron with an electric dipole moment superposed with it, corresponding to a little bulge of extra negative charge on one end of the spin axis and a little dent of negative charge on the other side. If all electrons look like this, with this asymmetric charge distribution aligned with its spin axis, you take a movie of this particle and run it backwards in time. Mathematically, that corresponds to a time reversal transformation. Then you'll see that the time-reversed version of the particle doesn't exist because the spin has changed direction, but the static electric charge distribution hasn't. So this obviously looks pretty exotic, not what you would expect from anything in quantum electrodynamics. And in fact, in relativistic quantum field theories, the most successful theories we have of fundamental physics, the combined symmetry of charge conjugation C, parity P, and time reversal T, that symmetry is always conserved. And therefore, any system that violates time reversal symmetry has to also violate CP symmetry in equal and opposite amount in order to keep CPT conserved. So time reversal symmetry violation and CP symmetry violation are equivalent, and I'll use the terms interchangeably. So, it's been understood for quite a long time that looking at CP violation in particle physics is a very powerful window to finding new particle physics phenomenon. So we know, for example, that CP symmetry is not a good symmetry of nature. It was observed already in the 60s in decays of K mesons that CP symmetry is violated. So there's nothing that protects it since it's already broken. And CP violation in these relativistic quantum field theories can always be parameterized by a complex phase, so just a simple number. In the standard model, the way the CP violation enters is through the quark mixing matrix, the fact that things like downstrange and bottom quarks can be mixed so that they interact with top quarks up quarks, and so on via the weak interaction. So this is a 3x3 unitary matrix that describes this mixing, and a general 3x3 unitary matrix you can always parameterize in a way that necessarily has to have the degree of freedom of a single complex number. And here's a particular parameterization of this matrix in the standard model that shows this complex number. And measurements on these K and B mesons and similar systems has shown that in the standard model, this one way that CP violation enters the theory through this term in the quark mixing matrix, the phase that's associated with that is almost exactly 1 radian. So it's not a small effect, it's a big effect. But the particular structure of the standard model of particle physics, the symmetries that are embedded inside it, in particular the partial symmetry between the down-type quarks, downstrange and bottom quarks, suppresses the observable effect of this CP violation in most systems. So the standard model is a little odd in that it violates CP symmetry, but in a way that even though it's naturally a big effect with a big complex phase, it shows up only as relatively small effects because of this additional symmetry. In contrast to that, if you take the standard model, that very successful model of everything we know about particle physics, and try to extend it, add new particles, new fields, then it's really quite ubiquitous that when you introduce these new degrees of freedom, you also introduce new places for complex numbers, for CP violating phases to appear. And it's quite difficult to prevent that from happening when you add new degrees of freedom. Of course, if you're a theorist, you can just say, I'm going to ignore these. But in fact, they're almost always there. It turns out that this is not a bug, but actually a feature, because it's been known already since the 50s from work from Sakharov that in order to explain the cosmological baryon asymmetry, that is the fact that the universe is made of matter and hardly at all of antimatter, violation of CP symmetry is required in order to explain that. And then later, Gavella showed that the CP violation in the standard model, this phase in the CKM quark mixing matrix, it creates CP violation that's too small to explain the measured asymmetry between matter and antimatter in the universe. So we know from experiment that there has to be some new physics that violates CP symmetry somewhere. We just don't know where. How does this relate quantitatively to particle physics? Well, we know just from simple QED that was worked out in the 50s that the electron can virtually emit and reabsorb a photon in a way that modifies its magnetic moment away from the bare value with G equals 2. It changes the G factor a little bit. But electrons can also virtually emit and reabsorb every other kind of particle that exists. For example, if it emits and reabsorbs a W boson, that'll also change the magnetic moment, the G factor. In addition, if an electron emits and reabsorbs new types of heavy particles virtually, and if those new particles are associated with some CP violating phase, then this can also cause the electric dipole moment of the electron to deviate from its bare value, which is 0. And it's easy to make a hand-waving sort of dimensionful argument about how big this effect can be. And essentially, it boils down to an electric dipole moment would be naturally about the size of a Bohr magneton times the sign of this CP violating phase times a dimensionless factor that scales like 1 over the mass squared of this new particle, and then times a dimensionless number that corresponds to how strongly the particle couples to the electron. If it's a photon, this would be the electric charge, and therefore give a factor of alpha. If it's other types of particles, these may be smaller numbers or larger. And even if a new particle doesn't couple directly to the electron, it can couple indirectly by the electron coupling to something known like a Z boson and then coupling to the new heavy particles, corresponding to a 2-loop Feynman diagram. And that corresponds to a higher order of perturbation theory and basically would reduce the prediction by another factor of the equivalent of the fine structure constant over 2 pi for the new coupling constants. If you put in the number from the experiment I'll tell you about that's made the best current limit on the electron-electric dipole moment, and if this arose at one loop order with a CP-violating phase, which is of order unity, like the only one we know of in nature, then you would see that we would have detected new particles with a mass of about 30 TeV already. And which is kind of amazing. The Large Hadron Collider can only see particles with mass of a couple of TeV. And as I'll explain, we're going to be able to go much, much further than this in the near future. It's also critical to this story that there is CP violation in the standard model that does lead to the electron having a non-zero electric dipole moment in the standard model. But again, the symmetries of the standard model, flavor symmetries and some more subtle symmetries, mean that the electron gets an electric dipole moment only at 4-loop order, so 4th order perturbation theory. And then when you sum up all the 4-loop Feynman diagrams, there are actually very severe cancellations in the sum over them. So that the bottom line is that there are many orders of magnitude of headroom where new theories of exotic particles would predict a non-zero electric dipole moment that's bigger than the one that we calculate for the standard model. So let me just, for folks who haven't heard this story before, emphasize just how sensitive these measurements are. So if you think of an electron as a ball of charge, that's not right, we know, but it is reasonable to think of the cloud of virtual photons around an electron. That actually has a legitimate size scale associated with it. It's about a femtometer. And to visualize it, suppose you blow up that cloud of virtual photons around an electron to the size of the Earth. And then say, how big of a bulge and a dent would we be able to see in our experiments on that scale? And if you take the best limit that I'll tell you about, you would conclude that we would have seen a slice 2 nanometers thin peeled off the southern hemisphere of the Earth and put it on the northern hemisphere. So whenever I think about these numbers, it's really kind of mind-boggling how sensitive they already are, but will continue to get better. So how do you do this? The basic idea is simple. The particles you're interested in typically start off unpolarized. We typically use some sort of technique, optical pumping or coherent population transfer, to spin polarize the electrons or other particles in a way that's linked to the polarization of the light. So here, for example, let's suppose we end up with spins all pointing sideways to the right. And of course, this is a superposition of spin up and spin down. For technical reasons, we apply a magnetic field. Semi-classically, that causes a torque that causes the spin to precess around the magnetic field at frequency mu b, or equivalently, that corresponds to an energy splitting between spin up and spin down of mu b, which you can think of as causing a spectroscopic signature. Then to look for the electric dipole moment along the spin, we apply an electric field. If the particle has an electric dipole moment, that exerts an additional torque and causes the spin to precess faster, or equivalently increases the Zeeman splitting, or equivalently shifts that spectral line a little bit. And then we flip the electric field back and forth and look for synchronous changes in this Zeeman splitting or this spectroscopic line as we flip the electric field back and forth. So from this picture, it's very easy to write a simple figure of merit for how the statistical sensitivity of an experiment like this is just the energy shift over the energy resolution. The energy shift is dipole moment times electric field. The energy resolution from the energy time uncertainty principle is just 1 over the coherence time per particle. But then if you measure a big ensemble of particles, you improve by a factor of the signal to noise. So bottom line, to make a sensitive experiment, you want the biggest possible electric field, particles with the longest possible coherence time, the largest signal rates, and run for as long as you can. That integration time is a factor that's limited essentially by how long graduate students are willing to sit in the lab and flip the electric field back and forth. We haven't come up with any clever way to increase that, but so I'll tell you about, we have been able to increase many of these other factors. And I'll also point out, this is just statistical sensitivity. For such sensitive experiments, very, very careful attention to systematic errors is required, and I'll just skip that part of the story for this talk. Okay, so a big breakthrough that's happened in the field in the last decade or so has been to perform these experiments in polar molecules. And the idea is very roughly that if you apply an external field to a polar molecule, the small energy splittings associated with rotational levels or similar kinds of level structures make it possible to fully polarize the molecule in an electric field. But then inside the molecule, where the valence electrons live, there's an extraordinarily big intramolecular field, much bigger than the field it takes to polarize the molecules. This is actually a subtle story that I'll skip entirely, but essentially, if you think about the electron, it's acted on by an effective electric field that grows very rapidly with the atomic number of the heaviest atom in the molecule, like Z cubed. And if you put in some numbers, for example, our experiment uses thorium oxide molecules, the effective electric field experienced by an electron inside this molecule is about 80 gigavolts per centimeter, much bigger than you can apply directly in the laboratory. But we only need to apply about 100 volts per centimeter to polarize our molecules so the electron feels this field. This is true not only for electrons, but also for nuclei inside molecules, which I'll mention a bit later. Okay, so the reason it took the field so long to start using molecules for these experiments, which have these gigantic fields, is because working with molecules is hard, and the techniques to do that have really improved over the last 15 or 20 years, and there's really an emphasis on making the molecules colder. So, for example, the rotational levels, low energy splittings between them that make molecules easy to electrically polarize means there's a Boltzmann distribution that tends to give you small signals when working from any individual quantum state. But if you can cool those internal states, you can get bigger signals. If you can slow down the molecules and decrease their velocity spread, then you can get narrower spectroscopic lines and better energy resolution. And sort of the ultimate view here is that if you can not only cool but also trap your molecules for extremely long observation times, and in principle to get the best possible energy resolution. So let me tell you about the latest experiment of this type that we've completed. We call it ACME. It's a collaboration between my group at U Chicago, and groups of John Doyle at Harvard and Jerry Gabriels at Northwestern. And here we're looking for the electron's electric dipole moment. This experiment is a little bigger than a typical AMO experiment. At any given time, we maybe have 5 or 6 students and postdocs working on it. And this is the integrated group over the roughly 5-year lifetime of building the experiment and operating it. So this molecule we picked specially to do this measurement. It has some very nice features. It has the largest known effective field for any molecule that people have actually worked with. It has a sufficiently long coherence time. It has a suppressed magnetic moment, which helps us be insensitive to magnetic noise and systematic errors, and some additional features that I won't go into. Surprisingly, this thorium oxide molecule has a ground state which is a singlet state, which means all the electron spins are paired off and cancel, but it also means all the electron-electric dipole moments are paired off and cancel. So we can't do a measurement in this singlet state. Instead, we do it in this metastable first excited state, which is a triplet state. So here there are 2 unpaired electron spins. One of them feels this large internal electric field. The other is effectively there to cancel the magnetic moment of the first one and also increase the polarizability of the molecule. So we populate this metastable state using a stirap process with 2 lasers, use a third laser to probe this state and detect what's happening in the state via laser-induced fluorescence. So very standard AMO techniques. Here's a schematic of what happens in the experiment. We start with a cryogenically cooled molecular beam source that creates a beam of thorium oxide molecules. Many rotational levels are still populated in the Boltzmann distribution, despite the fact that the temperature is only about 4 Kelvin. So we do some optical pumping or equivalently rotational cooling to compress the Boltzmann distribution a little bit. The molecules then fly into a magnetically shielded region where an electric field and magnetic field are applied parallel to each other. We populate the metastable state with about 80% efficiency from the ground state, and the polarizations of these lasers are transferred to the spin polarization of the molecule, so we know that the molecules are spin polarized in the direction that's perpendicular to the plane here. They travel for about 20 centimeters, corresponding to about a millisecond with just the electric and magnetic fields interacting with them. And then they reach the detection region downstream, where the difference between the scattering, the laser-induced fluorescence for polarizations along or against the spin helps us detect which direction the spin is pointing at the end of the experiment, and then collect the laser-induced fluorescence into photomultipliers with about 5% overall efficiency. So here's pictures of the ACME apparatus. It's all sort of normal size. This is about 1 meter. We have a few tables of lasers and a strange platform to direct laser beams vertically through the apparatus. But the bottom line is, in 2018, we delivered a result which was the best in the world and is already cutting into predictions of theories of physics beyond the standard model, shown here in various colored splotches. But of course, as our limits have gotten better and better, and the LHC has not seen anything outside the standard model, particle theorists are very inventive and come up with new models that say, oh, we said it was here, but actually we meant it's 2 orders of magnitude smaller. So keep looking. And well, this plot shows in a particular type of theory, supersymmetric theories, the y-axis is a plot of masses of new particles. Here are the heaviest standard model particles, the top quark and the Higgs boson, and these are all the possible supersymmetric partners of ordinary particles. The blue corresponds to direct limits from the LHC around 2018, and our experiments, first generation of ACME ruled out this range of masses. The second generation of ACME ruled out another higher range of masses. And notice the green bars here are what supersymmetric theories considered natural. So we've already blown by what the theorists 20 or even 10 years ago would have said are natural values for electric dipole moments, unfortunately. And also point out there's a totally different experiment looking for the electric dipole moment effectively of the Mercury 199 nucleus, which also sets important limits on partners of quarks. We're building the third generation of ACME with a number of improvements. Bottom line here is that we're anticipating somewhere between a factor of 10 and 30 improved sensitivity within the next 2 years or so. So this story is not finished. Here's the ACME 3 team, some of the same old folks and lots of new young folks. In the meantime, we've launched a new experiment we call Centrex, which uses a very similar principle to ACME, but now not to look for the electron's electric dipole moment, but to look for this nuclear shift moment, which is analogous to an electric dipole moment. And again, we try to take advantage of the huge intramolecular field now acting on a nucleus rather than on electrons. This is all done in a closed shell molecule. Well, right, the goal is to improve what's been done already in mercury atoms. And the apparatus that we're building now looks an awful lot like the ACME apparatus. It's based very heavily on it. So it's really underway. We're building lots of the modules and control systems needed for Centrex. Again, it's sort of big room scale experiment, much smaller than this room. And here's the Centrex team of collaborators and students and postdoc. So Centrex is ongoing. We expect to get a result that's a factor of a few better than the mercury limits within a couple of years. But it's worth noting that the state-of-the-art experiments, this mercury experiment for nuclear EDMs, ACME for the electron EDM, our friendly competitors at JILA also looking for the electron EDM. These experiments have all been ongoing for more than 10 years. None of them uses even laser cooling, which is kind of stunning for a modern atomic physics experiment. So there's long been a sense that being able to do this with colder molecules would be a big advantage. There's been enormous progress in the direct cooling of diatomic molecules since our group was able to first laser cool molecules and then magneto-optically trap them back in 2014. There's now a huge number of groups that are using these techniques, have gotten optically trapped molecules down at temperatures of around 10 microkelvin. So this is going rapidly, and many of these groups have a direct eye on trying to use these laser-cooled molecules to look for the electron's electric dipole moment. So the sort of best-case vision of this is if you could laser cool and trap molecules that are sensitive to the electric dipole moment of the electron, trap them in an optical lattice, choose a molecule that has a big effective field, somehow get very long coherence times for the electron, then you can imagine getting to something like 1,000 times better than we've already gotten with our ACME experiment. So this looks very promising. In the meantime, there's a whole other part of the field that instead of directly laser cooling and trapping molecules, instead starts with laser cooled and trapped atoms and binds them together to form molecules without heating them. These experiments I refer to as assembling ultra-cold molecules from ultra-cold atoms, and it's really extraordinarily successful. Now, at least a dozen groups have done this to get optically trapped gases and molecules with temperatures in the 100 nanokelvin regime, including some really brilliant work very recently from the MPQ group. So far, these have only been applied to molecules made of 2 alkali atoms. But those sorts of molecules, it's already been demonstrated that long nuclear spin coherence times can be demonstrated. These are all closed shell molecules, so not good for looking for the electron EDM, but good for looking for nuclear electric dipole moments. The bad news is that every one of these, every alkali pair molecule up to date has had poor sensitivity, a poor internal electric field. But we think we can fix that and also take advantage of a different property, which is the fact that certain very heavy nuclei, radioactive nuclei, have a peculiar shape called an octopole deformation, a sort of pear shape that enhances the nuclear EDM by factors of nearly 1,000 typically. So this has been something people have been trying to take advantage of for a while, but it's hard to work with radioactive species. Nevertheless, we think we've now found a way forward in this experiment by using the very strange sounding molecule francium silver. So it turns out that one can very efficiently trap even a small number of francium atoms made in radioactive decays, and then very efficiently turn trapped atoms into molecules, efficiencies of order unity. And these are both alkali atoms that can be manipulated in the same way as other alkali atoms. Francium, this particular isotope of francium has this big EDM enhancement. Trapping of francium and silver atoms has been done for over 20 years, and calculations from Timo Fleig at Toulouse have shown us that the intrinsic sensitivity is very high. So again here, now rather than hoping, we can simply say, okay, if we can make these molecules in the same way that people already make other bialkali systems, then we anticipate something like a factor of 300 or even 1,000 improvement beyond the current state of the art without having to really create any new technologies. This is just based on what other people have done with other species. In the long term, it may be possible to also employ spin squeezing to have the signal-to-noise scale not like square root of n, but linearly with n. And of course, you know, most folks in this audience are familiar with the concept of spin squeezing. Spin squeezing has been demonstrated already with several clock-like test systems, and it's long been understood that this is kind of a killer application for clocks. But another killer application for spin squeezing is to apply them to these electric dipole moment measurements. What's really intriguing is in the last year or so, there's been a series of papers pointing out that the strong polar nature of molecules can actually be used as a resource to engineer spin squeezing. So it looks like this system is a very natural way to apply spin squeezing. So with that, I'll stop and thank you for your attention and patience. I know I'm a little over time, but the bottom line is these searches for electric dipole moments really seem to be defining a new cutting edge of particle physics with the ability to probe energy scales very far above what the LHC can reach, but on short time scales. So, thank you.
Okay, so thanks, Dave, for this really interesting talk. Maybe we have time for one brief question. Yes, please.
Yeah, so maybe about this graphic actually. The shaded regions are the ones which are ruled out by your research?
Yes. Well, the purple shaded regions are already ruled out by our research or this Mercury experiment. The green regions are the expectations of experiments that are already underway, half built. So within the next 2 years, give or take. And then the blue and the orange would be for things that would incorporate laser cooling and trapping.
Okay, so the nuclear experiment you hinted upon in the end they are already included in this graphics.
So the nuclear experiment would be the orange arrow there. Yeah.
I see.
Yeah.
Thanks.